Okay guys, welcome to lecture 2 of quantum complexity theory for the winter 2020 offering at the University of Paderborn. So today's topic, basically speaking, is going to be a very quick review of basic linear algebra and quantum computation. With that said, let me just start with some very quick announcements, right? So tutorials are going to be starting next Tuesday, right? Those are going to be through Big Blue Button. Again, those will be private. For those registered in the course, you should have gotten your access code for Big Blue Button. Check Panda for your messages. The other point I want to make is that assignment 1 has been released. That is due before tutorial 1, and generally speaking, assignments will be due immediately before the next tutorial, basically, so that we can discuss the solutions in tutorial. Solutions will typically be released right before the tutorial begins. And just a heads up, please do submit your assignments via Panda. I strongly suggest that you do all your assignments in LaTeX. It's just great practice. It makes it easier for me to read, and if I'm in a good mood, then, you know, good things happen, right? Do things in LaTeX if you can. Be nice to your professors, right? That's all I want to say in terms of prelude. So today's lecture, by the way, if you have a look at the lecture notes, they're a bit over 11 pages long. Of course, this is way too long for us to cover in one lecture, and that's fine, because this is really supposed to be a total review lecture, and there's no way I'm going to cover every bit of these lecture notes. So I'm going to try and focus on the most important parts that I want to refresh your memory on. But really, for this lecture, it's very important that you take the time to go through the full lecture notes for this lecture to make sure you're not missing anything that maybe once upon a time you learned, but now you forgot. Okay, so that's my very clear disclaimer about this lecture, that we're not going to cover all the course notes for this lecture. Please do look at them yourself. Okay, so again, today's topic will be a bit of a linear algebra reminder and a bit of basic quantum computation reminder. And of course, we'll go a bit quick because it's a review lecture. So let me just start as usual with the quotes atop the lectures. The first is by our good friend Albert Einstein. It goes, "I think that a particle must have a separate reality independent of measurements. That is, an electron has spin, location, and so forth, even when it's not being measured. I like to think that the moon is there even if I'm not looking at it." Okay, so this is Albert talking about, this, I guess what's nowadays this very infamous controversy about quantum mechanics as a theory, right? Back in 1935 or so, there's this famous EPR paper that really posited that as a mathematical theory, quantum mechanics was either incorrect or incomplete, basically, right? It was missing something when it came to describing nature. And this is really due to things like entanglement that you would see showing up as far as the predictions of quantum mechanics go, right? And the second quote is by David Mermin. It says, "Experiments have now shown that what bothered Einstein is not a debatable point, but rather the observed behavior of the real world." Okay, so nowadays we have experiments like, loophole-free Bell inequality violations, basically, or experiments that detect these violations, basically, that really more or less conclusively show that, nature really does behave in a non-local fashion. Okay, there's really not much we can do about that, and that's fine, And again, let me be clear that, even though there has always been this very long-standing debate about what exactly quantum mechanics means, how do we interpret it, the math works, the science is correct. Okay. Okay. So last class, we reviewed basic complexity theory, because this is going to be a complexity theory course, right? And now I'm going to quickly go over linear algebra and quantum computation. So let's begin with linear algebra. As usual, there will be lots of exercises kind of peppered throughout the notes that I encourage you to do. And maybe I'll point out some of the more important ones as we go along today. So 1, linear algebra. Okay. So again, I'm just going to state kind of the important things. This is meant to be just a quick kind of brushing up. So in this course, remember, we deal with d-dimensional complex vectors, generally speaking, right? So these are vectors that live in CD. Each entry of this vector is a complex number, right? And remember, we call this ket psi. That's what this notation here means. Okay, that's the Dirac notation. And complex numbers, remember, we always write them in 2 ways. The first way is I can write a complex number c as either c equals to a plus bi, right? Where both a and b are just in the reals. Okay. And the other way I can write it is in polar form, which is typically the more useful fashion for us, but to each his or her own, right? And here again, r and theta are real numbers, just like before. And the complex conjugate, remember, let me just remind you, the complex conjugate of C is C star, right? And that either equals A minus BI, we put a minus sign there, or it equals to R to the E to the minus I theta. Okay, so we just put a minus wherever we see the I. I think it's always worth remembering, one of the reasons we like the polar decomposition is because we can view it, right, in this 2D imaginary, 2D complex plane. And so, each of these parameters, R and theta, have a very nice meaning, right? So here's my complex number, C, right? And we'll fill this in. Well, I guess I want it to be review. So R is this thing here. It's just the length of the vector, basically, right? So it's this thing. And theta, remember, is this angle with the x-axis. So it is a very nice geometric interpretation. The unit circle in particular will be kind of all the, well, I guess I didn't draw that, right? The unit circle will be, whenever I say unit circle, I'm always referring to all the complex numbers that basically, are on the circle that has norm 1. Okay, so all the vectors R, where R is 1, basically. Okay, and so if you're wondering how to convert between these two, remember the basic idea, sorry, not these two, but these two, although, I mean, it's equivalent, is that remember that the complex number C, in terms of the parameters you see over here, is going to be R times the cos of theta plus I sine theta. Right, so this is Euler's formula. Okay. So that's how you can convert between the polar form and kind of this more standard form. Okay, and let me just very briefly remind you that R over here, right? This R is really what we think of as the magnitude of the complex number, right? And this theta here, so this is what we call the magnitude, and theta is always what we call the phase. Okay, when we work in this polar form. Okay, and let me just remind you that if I have a complex number C first, the formula for this, what is C star C square root? Okay, and this generalizes the usual absolute value function. If I have a real number, if I square the real number first and then take the square root, I just get the absolute value, right? And this is how we generalize it to complex numbers. And in particular, if I take the absolute value of R e to the I theta, right? If you work through this, remember that what this will give you is, the number R, which we typically think of being as non-negative. I mean, it doesn't have to be, but you can suck up kind of the negative into the phase if you want. And then it will be times this. This is just the multiplicity of the absolute value function. And the norm of this is just equal to 1, right? I mean, that's just equal to R times the square root of e to the I minus theta times e to the I theta, right? So this is just the absolute value of R. And this is exactly what this picture suggests, right? That the magnitude of a complex number should be the length of this vector R. That's exactly what it is. Okay, so two very quick identities you always want to remember then is whenever if I have a complex number and I add it plus its complex conjugate, remember this is just going to be 2 times the real part of C. The imaginary part will be killed off. If you do it this way, you'll get 2 times the imaginary part of C. And then C plus C times C star is just what you see over here, which is absolute value of C squared. Okay, that's just essentially this definition here. Okay. So remember that if I have column vectors, I can also talk about row vectors, right? This was going to be, the bra of psi, right? And remember, all this was is I take the same vector, I had my column vector, and I put it on its side now, and I take stars, okay? Okay, so that's a row vector now. And since I have, once I have this bra operation and this ket vector, basically, if I just multiply them together using standard matrix multiplication rules, right, I would get psi times, I guess, well, let me just do it in the most generality, right? A bra vector times a psi vector. This is just going to be a complex number, right? This is, 1 by d, d by 1. So, the shorthand we'll usually use is just write it like this. And this will just be some complex number, right? Because you'll use the outer dimensions here, 1 by 1. And the formula now is what? Just from the matrix multiplication, actually, is the sum over I equals to 1 up to the dimension of psi I star phi I. Okay, so we immediately get the inner product, basically. And remember that once we have the inner product, now inner product is supposed to give me some notion of overlap, right? Remember, it tells me if I have two vectors, I want to know the inner product, then what you're really asking for is this, right? If I project one vector on the other, how long is this length over here? So once I have the inner product, I can then define a notion of length for a vector, right? I can take the inner product basically with itself. So then I can define the Euclidean norm, and we'll write it this way. And what is this? I just take remember the inner product of the vector with itself, and then just like the absolute value function, it's literally the high dimensional generalization, right? I mean, look at how we define absolute value up here, right? Whoops. Right? This is just the high dimensional generalization of that. And I take a square root, and that'll tell me the length of the vector. And I really want to stress that, I say the Euclidean norm, and I put this 2 here because that's a very special norm, right? This is probably the formula you've seen in high school. You can always generalize this to other types of norms. Let me just mention kind of the 2 most common ones, which we'll probably see again in this course, which are the 1 norm and the infinity norm. The 1 norm, what it does is it just sums over all the entries of psi I with an absolute value. Oops, sorry, no squared. And the infinity norm just tells me the maximum over all I of psi I. Okay? So in terms of in this picture, right, this right here would be the 2 norm. Let's just call this vector v. That's the 2 norm. It's the direct distance between the direct length in this. The 1 norm adds all the components individually. So the 1 norm in blue would be this thing plus this thing. Right? That would be the 1 norm. You'd add those 2 lengths together. And the infinity norm just tells me what is the largest component, right? So the infinity norm in this case would be the largest component. Let me do it in green, right? So it would just be literally this component in this case. Okay, blue will be this one, green is this one, and red is the 2 norm. Okay, so all the 3 different kinds of norms we'll probably see in this course, they all have different geometric meanings. Okay. So orthonormal bases, right? Remember that I'll say, of course now we've defined individual vectors. We can now talk about sets of vectors. So everything we do, of course, in this discussion will slowly keep building up on what we've just discussed. So remember an orthonormal basis is a set of vectors. Psi I is a subset of CD such that well, let me just do it this way. Psi I, the inner product of the ith vector and the jth vector, right, is equal to delta ij. Remember the Kronecker delta? Okay, and let me just remind you what this was, because we're going to certainly use it over and over again. This is 1 if I equals to j, 0 otherwise. Okay? So that's what an orthonormal basis is, right? Remember, always think of, for example, the x and y axes. Those will give you orthonormal bases if you normalize the vectors. If you don't want the vectors to be normalized, right? So like, why do I get a 1 here when I take the inner product of psi with itself? Well, because we're talking about an orthonormal basis. Remember, an orthogonal basis just means that we don't normalize the vectors. They're just going to have inner product 0. Okay, and the most common basis we'll use in this course is the standard basis, or sometimes called the computational basis. And remember, we'd label this thing as 0. 1 is the second one. All right, so you just kind of keep moving the 1 down in the vector. And the very last one is labeled d minus 1 because we started counting at 0. This is the standard basis, right? It's the most basic thing you could write down. Okay, so we'll see the standard basis over and over. And just remember that if I say, I could always rewrite any psi in complex T by definition as, and really I'm reviewing this more, I mean, I trust you're comfortable to some extent with linear algebra, but I just want to make sure that you remember the notation and how we play with it, right? So that's why I'm writing all this out again. I could always rewrite it as the sum over I equals to 0 up to d minus 1 of some complex amplitude, alpha I, times I, right? So I can always expand any base vector in the space in terms of any particular basis I've chosen, and here's one basis, I. And so remember that if psi is normalized, if it's a unit vector, then this implies that the sum over I of the sum of squared is just equal to 1. Okay, so that's the condition you should always keep in mind, particularly when we talk about quantum states. They're going to be normalized in this way. Good. So now we have vectors, we have sets of vectors, and now we want to play with the vectors. And that means we want to talk about linear maps. Okay. Now, a lot of times, at least when I was, let me be more clear. When I was an undergrad, learning about things like linear algebra, I was a lot more comfortable thinking in terms of matrices when it came to maps and things like this. But I really want to stress that you should try and think of linear maps as first and foremost as linear maps. Okay, and a matrix is really just kind of a consequence of the fact that the map is linear, right? It's not the primary form of the map in some sense. It's like a secondary form of the map. Okay, it just so happens that matrices are nice to work with, but you should always remember what it means for a map to be linear, and where the matrix comes from. Okay, so we'll say again that a map phi from CD to CD, right, takes a d-dimensional vector to a d-dimensional vector. That map is linear, right, if I plug in kind of any sum of vectors like this, psi I, and let me put some complex numbers in there. The key point is that the sum comes out. Right? That is the linearity property. It's this equality right here. And it's because of this property that we can talk about things like matrices. Okay? And this is crucial, by the way, this linearity property, right? Because if you didn't have linearity, then in principle, for any possible combination of vectors, you'd have to be able to define the action of the map possibly differently, right? And you can't do that. There are an uncountably infinite number of such combinations. But because the map is linear, all you have to do is you need to describe the action of the map on some nice set, like a pick your favorite basis, right? And that's enough to extend the action of the map, not just to your basis now, but to the entire space, to any combination of those states. And that's why that's where you use this equality. So in just some notation, I'll use this notation L of xy to note the set of linear maps from some space x to some space y. Okay. A lot of times I'll in fact just write L of x if the map takes you from x to x. If we're not switching spaces, then I'll leave it the same. Okay. So matrices are what we get out of linearity, in the sense that I can always now describe a linear map, and in this course everything is finite dimensional, as you've probably noticed so far. So I can always write down this finite size matrix to describe the full action of the map. So I can talk about the matrix representation of phi. Okay, and this is, I'm going to assume it's a map that takes you from d dimensions to d dimensions. Of course, you could generalize this definition. And I'll give this matrix a phi, a name like that. And it's going to be basically a d by d complex matrix. And what does A look like? Always remember this formula. It's very simple. Now, of course, you could write a matrix in any kind of basis with respect to any base you want. I'm going to write it with respect to the standard basis. What does that mean? That means that each column, the ith column, is nothing more than you take the ith standard basis vector and you apply the map to it. Okay, so the first vector, first column will be phi of 0. The second column will be phi of 1, right? All the way to the last column, which would be phi of technically d minus 1 because of the way we indexed our standard base vectors. Okay, so this is just a complex vector. It's got d columns because they're d-base vectors, and each column is dimension d itself. This is the formula. Once you know the action of the map on a basis, this is how you write down the matrix. Okay, so just as a quick exercise, let me do this one explicitly so that you have something concrete here during this review. Right? If I tell you, for example, that phi maps 0 to 1, and it maps 1 to 0, so it's basically the quantum NOT gate, right? It's flipping the bit. Then, the matrix representation of this, A of phi, is what? Well, the first column here is going to be 1, right? It's just the first equation I wrote down here, this one over here. And the second column will be this one, right? 0, just by definition. And what is ket 1? Ket 1, remember, is in a two-dimensional space. It's just going to be 0, 1. It's a second standard basis vector. And ket 0 is the first standard basis vector in a 2D space. And remember that this is what we call the Pauli X gate, okay? Named after Wolfgang Pauli, who was a physicist. So every now and then I'll try and remind you of basic tricks that are incredibly useful to save you lots of time. If I write down A times I, where I again is talking about a standard basis vector, remember that, okay, whenever I write ket and I put like one of these kind of Roman letters in here, like an I or something like this, then I'm talking about standard base vectors. If I don't want to talk about standard base vectors, typically I'll write like a Greek letter in there, like psi or something, okay? That's usually how you'll distinguish. So A of psi is nothing other than the ith column of A. Okay, so just keep this in mind. It just rips out literally the ith column. So for example, if I did x of 0, right, where I just defined x in the bottom right, this will pull out the first column, right, which in this case will be 0, 1. And it is nothing other than this one. Okay, so always keep this trick in mind. It will save you a lot of time. You don't have to multiply anything out to figure that out. Okay. Matrix multiplication. I'm not going to spend really any time on this, of course. I'm just going to give you the formula again. If I have two matrices, let's just say they're both d by d, then the product of two matrices, the ijth entry, remember, is the sum over, again, we're assuming d by d, a of I, comma, and I'm going to fill that in a second. Okay, and the common index is k. Right, so we might say that we contract over that common index k. There's a sum, and then that middle index kind of disappears. So that's how we define, remember, the entry of any, the ijth entry of a matrix multiplication A times B. And the key point I want to remind you of here is, remember, right, that matrix multiplication is not commutative. Okay, in English, right? It's not true that for all A and B, the product AB is the same as the product B times A. So this is in general. Okay, so that's something you should always keep in mind. And again, this is not some weird artifact of the mathematics. Like it turns out that what keeps matter stable in some very real sense is really this non-commutative nature of quantum mechanics, right? Otherwise, it turns out you'd have a problem. Okay, so that's actually very physically motivated and important for us. The terminology we'll use, if you're lucky, and the product of these two matrices, the order doesn't matter, we'll say that A and B commute. Okay, so that you'll probably hear throughout the semester. Often you'll define the so-called commutator A bracket B, and it just kind of captures AB minus BA, right? And so when they commute, this commutator is 0. Okay, so that's all I want to say about commutation. So, a very simple example. This is exercise 6. You can verify to yourself, for example, that the Pauli matrices do not commute, right? In fact, they anti-commute, meaning when you swap the order, it kicks out a minus sign. Okay, so now that I have matrices, let me define some important spaces for matrices, which we'll talk about fairly often. Again, I'll just give you quick definitions. So, number one, we have the image of a matrix, or more accurately of a map. Okay, so we'll define it as the image of A, right? It's a set of all, if I think of the map, right? I've got an input space and an output space for the map, and the image is basically this thing here, right? It's everything on the right-hand side in the output space that you can actually get to using this map. Okay, so it's a set of all vectors. Again, we're talking about CD on the right-hand side, so that there exists a vector on the left-hand side, which under the action of the map, whoops, this should be phi. If I take my map A and I apply it to phi, I end up at psi on the right. Okay, so it's essentially that red bubble. All the points down here don't have a partner on the left, so they're not part of the image. And kind of hand in hand with this notion of image, remember, goes this idea of the null space. A, right? And the null space is basically, so maybe these were points up here, right? That kind of aligns with the image on the right. But then you could have points down here, which, don't really go anywhere under the map. In fact, they get mapped to the scalar 0. And that is the null space. Null space of A is equal to the set of all d-dimensional vectors such that A times psi is the scalar 0. And something you'll hear me say often is, what is the rank of the matrix? Right? Remember, this is nothing other than the dimension of the image. Okay, so the rank in some sense tries to measure how big is this output space, right? What dimension does that red bubble on the right have? And there's a very nice relationship between these two called the rank nullity theorem. And that just basically states that the rank of A plus, which is the dimension of the image, right, plus the dimension of the null space, or sometimes called the nullity, I guess, that equals to the full dimension D. That takes up the full space. Okay? And that sort of makes sense because this kind of captures everybody who goes somewhere versus this captures everybody who doesn't go somewhere, who gets mapped to 0. Okay. So those are two important spaces we'll need over and over in the course. In terms of, operations on matrices, right? Though the main one we'll use, and I'll kind of redefine here, is the dagger or the adjoint operation, right? So this has various names. Remember, sometimes it's the conjugate transpose. I think in this course I'll typically call it the adjoint or the dagger because that's the symbol. But remember, this is you take the transpose of the matrix, and then you take the entry-wise complex conjugate. And it's very important to remember the formula, right? If I have the product of two matrices and I take a dagger, or I could also talk about the transpose. The dagger does distribute, but it swaps the order of the matrices. Okay, so it flips the order. Okay, so that's important to remember. So dagger is very common. We're going to use it all the time, right? In fact, that's what we use to go from a ket vector to a raw vector. But the other important operation we'll use is the trace. So here's maybe one. And number two, let's talk about the trace of a matrix A. Okay, what was that? Remember that the trace of a matrix A is going to be the sum of all the diagonal terms of the matrix. So now it's the sum over I equals 1 up to D, or yeah, let's use 1 up to D, of A, I. That's just the trace. It's very simple. Okay? So note in particular that the trace is linear. Okay, well, maybe it's not, well, it should be obvious by staring with this if you're comfortable with the definition of linearity, but it's a linear map. Okay, that's important. And, usually we'll use, TR to denote it. It's a map that will take you from, this, actually, should be a little bit more careful, right? It gives me a linear operator on D, like a D by D matrix. And it'll squish it down to a single number, like, that's it. Okay, so the trace is taking a matrix and kind of imploding it. And the trace is very nice because it has this so-called cyclic property. Remember that the trace of a product of three matrices A, B, C, normally I can't switch the order of matrix products, right? Doesn't play nicely. But the trace is very nice. It allows me to cyclically shift over, kind of move this guy over here if you like. Okay, equivalently, if you want, you could have moved the last one up here. Doesn't really matter, right? So that's very, very nice. And in particular, what this means is that the implication of this, right, is that the trace of AB always equals to the trace of BA. Okay, so even though kind of A and B don't necessarily have to commute, right, in terms of multiplication, when you take the trace, it's throwing out a lot of information, right? I mean, instead of taking the full product, it's squishing it down to one number, right? And under that very kind of restricted lens, the product AB looks identical to the product BA. Okay? So that's a very nice property of the trace that we'll, again, use over and over again. Good. So now we've talked about vectors, we've talked about matrices, we've talked about how to play with matrices, operations on them, and now, well, if you have your rules to play with something, you need to build that something to begin with, right? How do I construct matrices? And a really nice way of kind of constructing or writing down matrices is the so-called outer product formulation, I guess, or decomposition of a matrix. So the outer product is basically, remember, this is just kind of the brother or the sister of the inner product, right? So if I take two vectors sine phi, these are d-dimensional vectors, okay? Then their outer product is, well, the inner product we did bracket, right? And that took us to a scalar, right? The inner product would have looked like this, and it would have been in the complex numbers. But now I don't want to do this. Now I'm going to do the obvious thing, which is I'm going to kind of swap the order of the bra and the ket. First I'll take a ket, and then I'll take a bra, right? This thing was d by 1, that vector, and this is 1 by d. So matrix multiplication tells me I'll get something that's d by d, right? It's a linear operator that is a d by d matrix. Okay, so outer products may be a little bit scary the first time you see them, but they're incredibly useful. Let me give you an example of just how useful they are. It's great when you want to write down a very large matrix, but in a very succinct fashion, basically, right? I mean, the matrices we'll deal with, remember, are exponentially large in the number of qubits, so you can't write the full thing down. You need a succinct way of representing them, and that's what outer product notation is really, really good for. So let me show you a trick that kind of really harnesses the power of this notation. So first, well, before I do that, let me just remind you very briefly, like if I have this thing here, like outer product 1 and 0, remember that's just 0, 1, 1, 0, and so you get 0, 0, 1, 0. Okay, you just work out the multiplication of those two vectors, this is what you'll get. And there's a much more general formula, in fact. This is not a coincidence. Like, you'll notice that this is basically doing an indexing, right? It's saying that, in the second column, because I start counting at 1, so the second column, second row, first column, I should have a 1, right? A second row, so second row is this one, first column is this one, there's a 1 here, and everything else is 0. Okay, and that's what we're going to get in general, right? Is a 1 in position I, comma, j, 0 elsewhere. Okay, that's the power of this product, outer product notation. I can very succinctly write down, this sort of standard basis, if you will, for the matrix space. And here's a trick, right? Remember that if I take a matrix A and I sandwich it, right, so that, this is d by d, right? This thing here, however, is d by 1, and this is 1 by d. So remember, this will give you a scalar. What will I get? Well, what I can do is, because of this property here, right? This is just kind of a matrix space, a matrix basis element, right? It just puts a 1 precisely in position ij of the matrix and 0 everywhere else. I can always expand this A out over here as the sum over I and j going over, let me make sure I'm consistent with my notation here. Oh, sorry, I want I prime, j prime, right? Maybe I won't bother writing indices down. And I go over all the entries of the matrix at position I prime, j prime. And to insert that in the right spot, right, I can use this outer product notation, right? I just put down the I prime, j prime matrix basis element, right? I can just expand out A that way. So a very succinct way of writing down A, right? And now I just use the fact that, the standard basis is an orthonormal, remember, to rewrite this as I prime, j prime, A of I prime, j prime, I prime, j prime, j. And this thing here, remember, these are orthonormal vectors, right? So you get a Kronecker delta showing up. And so the only term that will survive this double sum is when I equals to I prime, j equals to j prime, and that is nothing other than I comma j. Okay, and if you compare that with where we started here, right? And we ended up here. Well, the ijth entry of A, when A is written in the standard basis, is nothing other than take A and sandwich it with bra I, get j. Okay, so these tricks here using the outer product notation will save you a lot of time. You can just kind of stare at this expression and immediately know what it's talking about without actually doing any multiplication. Okay, just look up the entry ij of the matrix. Okay. And so now I just want to do a little bit of exercise 9. Just to rewrite, if I have the trace of a matrix A, remember, what was that? It's the sum of AII. And now I could rewrite this using the outer product notation. And I want to do this, well, I guess it's technically using the outer, well, I'm not sure if it counts using the outer product notation, but it uses the trick I just taught you, which is that AII, right? If I look at this trick we learned right here, what is that? Well, just sum over I of take I and sandwich it on the left and right with the ith standard basis vector. And that's the same thing as extracting out the diagonal entries. And this is it may seem kind of like superfluous, like why in the world do I care to rewrite it this way? Well, when I go to define the partial trace in this lecture, remember that this definition of the trace will be a lot more useful than this one. Okay, so we're going to use it we're going to base that partial trace definition on this definition you see here in terms of this bracket. So that's why I'm taking the time to remind you of that. Okay, so outer products allow us to take vectors and together put them together like Lego blocks to get matrices. And I'm done talking about products. Now we talk about eigenvalues and eigenvectors, which I always have a little bit of fun introducing in Germany, because the words eigenvalue and eigenvector come from German, right? I mean, eigen means kind of own, right? That's the German word there. So remember that any matrix, right, will have at least one eigenvector. Okay, and in particular in our cases, our matrices are going to be very nice. They're going to be what we'll call normal matrices, remember, so they'll always have a lot of nice eigenvectors, in fact. I'll say more in a second. But remember that if I have a matrix A it's a linear operator, it's a D by D matrix, I'll say that it has an eigenvector, an evec for short, psi, if A times psi equals to lambda times psi. Okay, and lambda is what? It's a scalar, and it's the so-called eval or eigenvalue. Okay, so these come in pairs, right? Psi and the eigenvalue, lambda, come in pairs. And so as a cute exercise, it is always good to remember what are the eigenvalues, especially what are the evecs? This is exercise 10, essentially. What are the eigenvectors and eigenvalues of, say, the Pauli X operator? This we'll use all the time in this course. And the Pauli Z operator, which is 1, 0, 0, minus 1. Okay, what are the eigenvectors and eigenvalues of those? So diagonal matrices like Z are very easy. The eigenvectors are the basis in which you've just written the matrix, which in this case is the standard basis, right? I'm assuming all the matrices I write down are in the standard basis here. So the eigenvectors of this would just be ket 0 and ket 1, the two standard basis vectors. And the eigenvalues are sitting on the diagonal, right? Remember, they're just going to be 1 and minus 1. And this is true more generally, right? If I have a matrix which, is, say, upper triangular, the eigenvalues will always be on the diagonal. Okay, in this case, it's not just upper triangular, it's actually diagonal, so I had a 0 here as well, but so long as, either below or above the diagonal is 0, then you'll get the eigenvalues on the diagonal. So that's a very easy way to immediately recognize, okay, those are the eigenvalues. The X operator, remember, is a little bit trickier, but here you can take a guess. Okay, and remember that what does X do? It's like a NOT gate, it maps 0 to 1, 1 to 0. So what is X going to act invariantly on? Well, remember that it'll act invariantly on the so-called plus state, which is this one. If I kind of add an equal superposition of 0 and 1, right, then this is just going to equal to, and the notation I'll use, let me remind you, the plus state is by definition this thing in this course. It's just a plus state again, right? The eigenvector is plus, and in front we have a hiding, the scalar 1, that's the eigenvalue. And if I do the exact same thing here, but now I put a minus sign, then remember that, so X times, this is the minus state by definition. Then we'll get minus 1 times ket minus. Okay, so the eigenvectors of X, remember, are plus minus, the state's plus minus. And the eigenvalues are going to be plus 1 and minus 1. Okay, so we'll use that fact all the time, as well as the spectral decomposition of Z. Okay. Sorry, I grew up in Canada, so that means that I'm going to say Z instead of Z. That's life, I guess. So the nice thing about the types of operators we're going to work with now are that you can always decompose them very nicely because they come from the special class in terms of something called the spectral decomposition. So let me remind you what that is. Okay? So an operator A is normal if and only if A dagger equals to A dagger A. So if you multiply by its adjoint, it's the same thing as if you reverse the order of the multiplication. And this is, it turns out this is also if and only if. Okay, if and only if. A has something called a spectral decomposition, and this is super useful. Anytime you try and do a proof in this course, you start with the spectral decomposition typically, or at least think if you could use it. And all this means is you write the sum over I, lambda I, these are the eigenvalues of the matrix, and then eigenvectors. And I'll write the eigenvectors as lambda I in a ket to denote that this is the eigenvector corresponding to the eigenvalue lambda I. Okay? So any normal operator, which is pretty much every operator we'll see in this course, can always be diagonalized in this way. Okay, and let me be clear that if A is normal, then the evex can be chosen as an orthonormal basis. So this, in this course, in order to preserve my sanity, will denote orthonormal. Okay? So we can always assume that the eigenvectors are orthonormal. If you go beyond normal operators, you can still have a full dimensional basis of eigenvectors, but they might be, say, linearly independent instead of orthogonal. But typically we won't see that in this course. Okay, and now, now that I know that a normal operator can be decomposed this way, we can write the trace operation in yet another nice way, right? If A is normal, then the trace of A, what is that? So remember that let's write it this way. It's the trace of, and here I'm just going to plug in the spectral decomposition of A, right? I can always write it this way. All right, and the goal here is now we're trying to say, can we conclude a connection between this trace operation, which just adds up diagonal entries, and the eigenvalues of the matrix. And as a kind of a hint, as a heads up, right? If I had an upper triangular matrix, the trace would just add up lambda 1, lambda 2, and so forth. And I also told you that if the matrix is upper triangular, then these are in fact the eigenvalues, right? So literally the trace is just the sum of the eigenvalues for an upper triangular matrix. So you might wonder if this is coincidence, or does this hold more generally? And the answer is that it actually always holds, whether or not your matrix is diagonal. Okay, so even if your diagonal entries are not the eigenvalues, you will always have that the trace is equal to the sum of the eigenvalues. Okay, so let's see that. Here I could write this. So why is this true? Take a moment to think about it. Why did I just move kind of this sum out over here? By the way, let me also write down the reasoning for these. Okay, why does this hold? Well, because the trace is linear, right? I can move the sum in and out. And so what is this equal to? Well, then this is just the sum over I, lambda I, and the trace is cyclic, so you can move, turn the bra ket into a ket bra. And this is an orthonormal basis, the lambda I, so the inner product will be 1. And so you get exactly what I claimed, which is that the trace of the operator is nothing other than the sum of the eigenvalues. Okay? Even if the matrix is not diagonal as written and the eigenvalues are not on the diagonal. So again, that's the power of this spectral decomposition. Notice how, to do this calculation, I did not need to know anything about the actual eigenvalues or eigenvectors. I just generically did the computation. Okay. Let me just state the next exercise because we'll kind of use this all the time. But I won't do the exercise. Again, I'll let you do this. Sorry, this exercise 12 in the notes. So if A is diagonalizable, maybe let's just say, okay, maybe let's make it a little bit easier. Let's just say if A is normal, right, then the rank of A, prove to me that the rank of A is equal to the number of non-zero evals of A. Okay, so take a moment to do this exercise. It's very important. It will make sure you're comfortable with things like the spectral decomposition. Hint, hint, start with the spectral decomposition, right? Good. So now I've kind of defined all sorts of operations on matrices and eigenvalues and eigenvectors. The last two things we want to cover before we go to basic quantum computation is, let me remind you of some important classes of matrices which we're going to use all the time. And then I will define the notion of an operator function. And then we'll be ready to talk about quantum computation. Important classes of matrices. Whoops. Double oops. All right. So what matrices will we see over and over? Each of these will generalize a class of real numbers, by the way. Okay? So I'll start with, not necessarily the most general one, but unitary matrices. Remember, these are going to be the ones that dictate what quantum gates are allowed. Unitary matrices are the quantum gates, essentially. And so this was just some operator which is d-dimensional. It has to be squared to be unitary. And I'll let you think about why this is true. So U is unitary if U dagger equals identity. And it turns out that once you have this, then you can also reverse the order. Okay, so that's kind of, the left side is all you need, in fact, to derive the right side of this. So in other words, all this is saying is that unitary matrices are extremely nice. They always have an inverse. And that inverse is, remember, super simple to write down. I don't have to do any sort of weird, dealing with polynomials and roots and things like this. All I have to do is take the dagger of this matrix. Okay? Okay, and I'll leave this to you, exercise 13. The eigenvalues of unitary operators are always on the unit circle. Okay, they look like e to the I theta for some theta. They always look that way. Okay? So in other words, you should think of the unitary matrices as kind of like a high dimensional generalization of unit complex numbers. And that's kind of the name of the game for these three classes of matrix I want to talk about, right? They're all going to be higher dimensional generalizations of some class of numbers you already know about. Okay, so number one, unitary matrices, they're always invertible, and the inverse is super nice. Number two, hermitian matrices. Maybe I don't need to write matrices each time. Okay. So a hermitian matrix is, let me just maybe use H for this. It's a linear operator from CD to CD. It also has to be square. If H equals to its dagger. Okay, so remember this just meant that if I take the adjoint map, the matrix stays unchanged. Okay. I have to double check this. So in my notes here I've written that to get an orthonormal basis for an operator, you have to actually be Hermitian, not just normal. I forget what exactly is the case. I'll double check that. But do be aware that the notes are maybe slightly contradictory right now between this section and just before when I was talking about spectral decomposition. So I'll have to clean up the notes for that. Regardless, for Hermitian operators, we can always assume for sure that the eigenvectors are going to be orthonormal. Just some notes. The set of Hermitian ops will be denoted Hermitian of x. Okay, so these are the set of Hermitian operators that map x back to x. I meant to do this also for unitaries. So the set of unitary ops I'm going to write as kind of this calligraphic x on x. Okay, just let me mark some typos quickly so I could fix these later. Okay, great. And Hermitian operators, what do they generalize? Well, their eigenvalues, you can show, are always in the real numbers. Okay? So in this sense, these guys are a high-dimensional generalization of the real numbers. So they generalize real numbers. All right. The third set, okay, I lied. There are 4 sets of operators we're going to define. The third one is the positive operators. We might call them positive semi-definite. Okay? And this is just going to be a Hermitian matrix. So Hermitian are going to be the biggest class. Like unitary is kind of different because it has complex eigenvalues, but henceforth everything I talk about will have only real eigenvalues in this section. So Hermitian is the biggest. The eigenvalues are real. Next, you can say the eigenvalues are real, but they're non-negative, and that's going to give you the positive operators now. So Hermitian plus non-negative, or just, I could say, strictly positive evals. Okay, and the first one will be positive semi-definite. Okay, that's the name. And the second one will just be positive definite. Right, so these are the 2 names you see over here, right? Semi-definite versus definite. That's the distinction. Semi-definite means the eigenvalues can be 0 as well. Positive definite means you have only non-negative positive eigenvalues, so you're full rank. You're an invertible matrix. Right? Remember that if you are rank deficient, if one of your eigenvalues is 0, you're not invertible. Okay. So normally, the notation we'll use for this, which is super easy to remember, is, whoops, maybe I'll just leave it and write it here. For positive semi-definite, we say that h is this kind of squiggly greater than or equal to, and for positive definite, we use the strict inequality. Again, it's kind of a squiggly one. So these are generalized inequalities that are defined on Hermitian operators. Okay. And this has generally speaking, if I ever write in this course like a is greater than or equal to b, that's completely equivalent to saying that a minus b is positive semi-definite. Okay, that's the way you should interpret that inequality. That's how it's defined. So as an operator, a minus b only has non-negative eigenvalues. So these things generalize the sets of non-negative and just positive reals. Okay, so that's what you should think about positive operators as generalizing. And remember the last kind of the smallest set we can go to is, well, now imagine you have not just non-negative eigenvalues, but just 0, 1, just like a bit. Okay. Then you get to these so-called orthogonal projections. That's the generalization of that. Okay? And all this thing says is that we have a linear operator pi. Sorry, this is an element of course. A linear operator pi, it's a d by d matrix, such that pi is Hermitian. So again, you start with Hermitian, then you go to the smaller set of PSD or positive operators, then you go to yet the smaller set of projections, such that pi is Hermitian and pi squared is equal to pi. Okay? So when you square it, nothing happens beyond the first application. And the fact that pi squared equals to pi, and the fact that it's Hermitian, take the spectral decomposition, you'll see that the eigenvalues of a projection are always in 0, 1. Okay, so in this sense, projections generalize the bit 0, 1. Sorry, here, the set of positive operators, the notation I'll use here is just POS, positive, on X. Okay. Don't think we have that for projections. Okay. And if you look at the spectral decomposition of one of these projections, remember that the eigenvalues are all 0 and 1, so the spectral decomposition is always really easy to write down, right? The eigenvalues are always 1. I mean, or 0, and then you don't even see this thing in the spectral decomposition. So it's just going to look like this for right? So you could always write it in terms of its spectral decomposition as an orthonormal basis. And this is vice versa. If I take any orthonormal basis or subset of such a basis and I write it this way, then what I will get by definition will be a projector. So that's what we should always remember in this course. And let me just remind you that a rank 1 projector, meaning it has only one non-negative eigenvalue, just staring at the spectral decomposition above, it's going to look like this, right? You take one single unit vector and you take ket of it. Okay, so that's a projector. And remember, a projector basically kind of projects you down or pushes you down into some low-dimensional space. Okay? And that's why intuitively when you run the projector twice, it does nothing the second time. So for example, the projector might project you down onto the span of, say, 0 and 1 and cut off the third dimension too. But once you're already in the span of 0, 1, if I try and push you down there again, well, you're already in that space. Where are you going to go now, right? Good. That's all I want to say about special operators. The last bit of linear algebra I want to give you is just to remind you of operator functions. All right. So an operator function, remember, is just what happens when we have a nice function that we know how to apply on the reals, like maybe the square root or something like this, or the absolute value. And now we want to extend that definition to matrices somehow. And so how do you do it? Well, there are many ways you could do it. So this is, how to apply a function f, which maps from the reals to the reals, to matrices, right? That's the name of the game. So maybe you want to apply, f of x could, for example, be the square root of x. So what does it mean to take the square root of a matrix now? And remember, the idea here is that you can do this for Hermitian matrix. So for H being a Hermitian operator. And whenever I write W bar, that's my lazy way of writing with in this course. So a Hermitian operator with a spectral decomposition, H equals to the sum over I, lambda I, and now ket bra lambda I. The generic definition of an operator function will be f of h as an operator, right? What is that? And remember, of course, what we want to do is, the signature for this function is take me from a Hermitian operator on CD to a Hermitian operator on CD. Okay, so because we're reviewing matrices, especially Hermitian operators are high-dimensional generalizations of real numbers, then it makes sense to think about high-dimensional generalizations of the functions that act on the real numbers. And what is that? It's just going to be the spectral decomposition we had over here, right? And I'll write down the eigenvectors. That doesn't change. Why does it not change? Well, I have no idea what it means to apply this function to a vector, but I know how to apply it to a scalar, right? And in particular, I can apply it to each of the eigenvalues. That's an operator function. Okay, so in the notes, I'll remind you, or I do remind you basically, why this is a meaningful definition and why it kind of does what we want. In the interest of time, let me just get you to maybe prove to yourself that if I consider f of h to be e of h, right? So the function here, sorry, maybe I should start with, the real valued version of the function is just the exponential. Whoops. So that's obviously not a proof. Prove that f of h is equal to e to the h, right? And what is e to the h? Well, e to the h, okay, well, I don't want to have to go through defining all this stuff again. Okay, maybe I'll, so the shorthand we'll use is e to the h, right? But what does that actually mean, right? In equation 13, this is really just identity plus h squared over 2 factorial plus h cubed over 3 factorial, and so forth. That's the definition we give it. And if you stare at this long enough, you'll see that this is nothing other than kind of the matrix analog of the Taylor series expansion for e to the x. Because e to the x equals to, the sum over n equals to 0 up to infinity of x to the n over n factorial. Okay? And so go ahead and prove that, if you do this definition in terms of applying the function to the eigenvalues, really, when you do, f of h, then you really will get this sort of Taylor expansion now in terms of the matrix. Okay, but again, this is review material, so I don't want to say more. That's exercise 19 in the notes. One thing I very briefly want to mention is exercise 22. Think about, let's even think about the square root function, right? F of x equals to the square root of x. And now think about suppose I apply now square root of identity as a matrix, right? Think about the identity 2 by 2 matrix, right? Square root of 1, 0, 0, 1, right? If I were to write it out fully. Well, the eigenvalues are sitting there, right? As an operator function, you just apply it to the eigenvalues. So square root of 1, square root of 1, right? I can only do this because it's a diagonal matrix. And what are the what are the possible square roots of 1? Well, there are 2 square roots of 1, right? So the possible choices, right, are what? Well, either the identity itself is a square root of itself, right? Or I could do minus 1, 1. Or I could do minus 1, minus 1. Or I could do 1, minus 1, right? All of these are square roots of the matrix identity. Okay, so these operating functions don't have to be uniquely defined. All of these are valid square roots of I, and in some cases, one might be more applicable than another to use, let's say. Okay, so that caps our review of linear algebra, and now we can move to the second half of the lecture, which will be section 2, which is going to review basic quantum computation. And again, if you're maybe not super comfortable with this, you haven't quite studied it before, I do recommend you to go back to our Introduction to Quantum Computation course, which was offered in the last semester. And again, you're going to find there lecture notes and videos for that. So that'll help you get up to speed if you find yourself a little bit confused. Okay. So remember that in quantum computation, there'll be kind of 2 notions of states, right? Pure states and mixed states, right? Where a pure state is kind of like saying classically, I have a string x, right? And I know exactly which string I have. And a mixed state is basically like saying, I don't have one particular string, but rather I'm going to flip a coin, and based on the outcome of the coin, I'm going to get a string, right? Meaning, I don't have a fixed string, I have a distribution over strings, right? That's the classical analogy you should keep in mind between pure states and mixed states, okay? So normally, and just like we'll do today, one starts by talking about pure state quantum computation, which just basically means that I know exactly what state I have in my possession, okay? I mean, of course, I can still do measurements on the state, and there will still be some probabilistic outcomes there. But in terms of, in principle, I could write down a full description of the state that exactly is what I have in my possession. Okay, so it's like having a fixed string in your possession. So remember that a d-dimensional pure state is represented by, well, just the vectors we've been playing with, right? Some psi. Let me write it out in this way. I equals to 0 up to d minus 1. And I'll write it as an expression in terms of amplitudes alpha I, standard basis vectors, and now this lives in CD, okay? And because it's d-dimensional, we'll call this thing a q-dit, right, in general. If we're talking about dimension 2, d equals 2, then that's when we talk about q-bits, remember, okay? Okay, and remember that, in this course we're going to adopt this so-called Copenhagen interpretation of quantum mechanics, which states that I really think of this vector psi as being simultaneously in all the base states alpha I, with some quote-unquote weight alpha I, okay? Okay, so remember these are amplitudes, and typically for us d is 2. Okay, we'll talk about qubits. So that's an individual kind of quantum system on its own. It's some d-dimensional state. Oh yeah, and we of course generally speaking want the norm of this thing to be 1. Okay, so that's always true for a quantum state. And we'll see kind of why, or we'll remind you why when we get to measurements. Good, so quantum states are just these giant vectors now. And so remember that, once I have these toys, now I want to play with them, right? So what am I allowed to do with my toys? Well, you're allowed to apply quantum gates which correspond to unitary operators. Okay, so I have a vector, right? And the type of matrices I can multiply by are precisely the unitary matrices which we've defined. Okay? So the set of allowable operations are basically the unitary matrices. Okay, we introduced this funny notation of kind of the tilde or the script U, CD. And remember, this meant that U dagger U equals to identity. Well, okay, technically, I guess the original definition looks like this. And these are the unitary operators. Okay? So in particular, what this tells us is that in quantum computation, the gates are all unitary, so they're all reversible, right? By definition, by nature, forces everything to be reversible, at least when you kind of look at the pure state picture. Okay, so I'm not taking into account things like noise from the environment here. Okay, so for d equals to 2, for single qubit systems, right, what are the common gates we see? Well, we already know Pauli x, y, z. Let me remind you what those look like. So x was this one, the quantum NOT gate. Z is this one, it's the quantum phase gate. And y is this funny operator that looks a lot like x, but it's actually not like x at all, right? I mean, they're orthonormal matrices in a well-defined sense. So those are the 3 Pauli operators. And I guess a good way of seeing that is if you kind of visualize these operators, I'm probably going to mess up because I haven't done this in a while, but typically, one likes to draw this block sphere where we think of the eigenvectors of each of these operators as, plus maybe is coming out at you, minus is going this way, and then you can write out the eigenvectors of the z operator, which are 0 and 1, and then the eigenvectors of the y operator, which are a little bit nastier, which I won't write out, but I think it's like 0 plus I1, 0 minus I1. They would be these vertical axes, right? So this is me being really bad at drawing. The idea is that, these axes basically form a 3-dimensional space in some sense, right? They're all going to be kind of orthogonal to each other, these eigenvectors. That's not entirely true. They're mutually unbiased technically. But they have this nice way of splitting the space up, I will. I don't want to call them orthogonal because they're not. The inner product of 0 and plus is not 0. Okay. Okay. So technically, I think this is something like 0 plus I1 up to scaling, and this should be 0 minus I1. Something like this. I probably didn't quite draw them right, but, look up block sphere if you're interested to remind yourself more about this. Okay, but there is a nice relationship between those 3. That's why I wanted to point that out. The other thing that's really nice, by the way, is that taken together, we also have identity, right? Taken together, these guys form a basis for the space of Hermitian operators, right? So these guys form a matrix basis for hermitian operators acting on C2. Okay, so what do I mean by that? That means that, i.e. any hermitian operator, and I don't think this is in the notes, but it's always good to know, can be written H equals 2, so some real number times identity plus some real number times x plus some real number times y plus some real number times z. Okay? Pretty sure that's true. You might need to put inject an I in front of these somewhere. But generally speaking, these are a basis for the hermitian operator space. Okay, and these you could allow to be reals in general. Okay, and I think if you want to talk about more general operators, like say maybe normal operators or something, you might need to go beyond the real numbers as coefficients, but it's been a little while since I thought about that. But certainly these guys form a basis for the space of 2x2 hermitian operators, and that's really nice to know. Okay, the other matrix I do want to remind you of is the Hadamard, the fourth matrix in play, and it's a bit different from the other ones. This is just 1, 1, 1, minus 1. Okay? And the Hadamard, remember, was very nice because, remember, the Hadamard takes us in and out of the, it introduces superposition, right? It takes us out of the standard basis. So the Hadamard to 0 took us to plus. The Hadamard to 1 took us to minus. And let me just remind you, since it's the first lecture, this is 0, 1, 0, minus 1, right? So this is kind of the most basic superposition of two terms, 0 and 1 now in the quantum realm. Okay, and the Hadamard is self-inverse, so if I play the Hadamard twice, it will undo itself. Okay, and that you can see because the dagger of H, it's certainly symmetric, the transpose looks the same, and all the entries are real, so taking the complex conjugate entry-wise doesn't change anything. So H equals its inverse, H dagger. Okay, one thing to remind you of, relative phase. Okay? So if I look at something like the Z operator, right, what does Z do? Well, remember that the Z operator maps 0 to itself, and it maps 1 to minus 1. Right? I mean, that you can just sort of read off by looking at the matrix. But if I do Z times plus, right, what is it going to do? Well, it's going to look like this, right? It's going to look like 1 over root 2 Z times 0 plus 1 over root 2 Z times 1, right? And then you're going to get the minus state out, right? It's going to put a minus sign in front of the 1. Okay, and likewise, if I do Z on the minus state, it turns out I'll get the plus state. Okay, so there's something very nice here that is worth remembering, which is that in the standard basis, the Z acts like a phase gate. Sorry, I didn't. I'll say that I'll say what I wanted to say. There are two things I really want to say here, I suppose. And here it acts like a NOT gate, right? With respect to the plus-minus basis, the Z operator acts like a NOT gate, right? It takes plus to minus and minus back to plus, right? So kind of the way we interpret these gates is really basis dependent. It depends on what basis you're acting on. Now, with that said, I just, why did I write relative phase? Well, it's because over here, right? When I look at this state here, right, it's 1 over root 2 times 0 plus 1 over root 2, and now, Z times 1, it's just minus 1, right? By definition of Z. And this is a relative phase because, I have a minus sign in here now. Minus 1 over root 2. And the point is that I can't just factor the minus out, right? So if I had some sort of phase where no matter what I factor out as a scalar in front, that phase doesn't really disappear, that's a relative phase. And I want you to contrast this with, remember, a global phase, which would be something like this if I had, like e to the I, e to the I theta 0 plus e to the I theta 1, right? I can factor this phase fully out, right? It's really the same thing as e to the I theta times, 0 plus 1, right? And in this case, that we would call a global phase. Anything I could just rip right out of the full vector, that's a global phase. And remember, the reason why we care about this is that a global phase cannot be detected in experiment. Again, that we'll see, when you get to measurement. When we start taking Baroquette of things, the global phases will just fully disappear. They don't change measurement statistics at all. Relative phases are very important, crucial to measurement. Okay, so MSMT in this course, measurement. Okay, so relative phases are very important. All right. Okay, a nice exercise for you to do, exercise 25, is that each of these gates, x, y, z, the Pauli operators, and h, they're all self-inverse, meaning if you apply them twice in a row, they undo themselves. This is not true in general of unitary operators, but for these four, it's true. Okay? So that's a nice exercise. I encourage you to do that. Again, exercise 25. Now, I've defined the types of gates we're allowed to use, and now we just review how we draw these things physically. And this is very much like the classical setting when we talk about circuits. Okay, so for example, I might do psi and then apply Pauli X to it, right? That's an X gate circuit. I might do psi and then I apply a Hadamard gate to it. Or I could do something else, right? I could do X followed by Hadamard. Okay, those are all circuits. We just have wires that the gates act on. In this picture, I'm assuming each wire is a single qubit, but they could be higher dimensional states if you want as well. And just as a sanity check, what state is this technically if I write it algebraically? Well, it's the state psi. I start with psi and then I apply X, right? Here I start with psi, right? And I apply H. And now here you have to be just a bit careful, right? Intuitively, you might think I should write down XH because that's the order in which the gates appear, but think about it in terms of temporally, right? In terms of time, psi first goes through X, then goes through H. So the first gate I apply is X, and then the second gate I apply is H. Okay, so the order is backwards in the algebraic formulation than it is compared to the circuit formulation. Okay. So this is exercise 26. What gate does this circuit simulate? Okay, so imagine I have a circuit. I do a Hadamard, followed by a Pauli X, followed by a Hadamard, right? And if you want, pick your favorite starting state. I don't really care. The point is, what unitary does this thing? What unitary is this really jointly? If I multiply out these matrices, right? And I'll let you think about that. The hint I'm going to use is, don't actually multiply things out. Try and figure it out that way. Think in terms of spectral decompositions. In terms of, X and Z. Okay, look at their spectral decompositions and see if you could figure out the answer. Okay? Okay, so that's what I want to say about gates. Okay, that's what you're allowed to do on a single quantum system. And now, of course, you might get bored playing with just a single quantum system, so now we want to talk about multiple or composite quantum systems. Okay. And for this, remember, we use this idea of a tensor product operation, right? It takes, we use the tensor product. And what this did is that, this is the so-called X-Men symbol, right? It takes in two vectors, one from dimension, say, D1, and one from dimension D2, right? So it takes two vectors. That's why I have this cross product in the middle. And it maps it to one bigger vector of dimension D1 times d2. Okay? So the dimension blows up multiplicatively. Okay, so, formally, okay, maybe I'll draw it here. Formally, if I have the tensor product of two vectors, psi and phi, right, and I look up position I comma j of that, right, that's defined as psi I, the ith entry of I, times the jth entry of phi. This is the way we actually define the tensor product map, okay, entry-wise. Okay, so again, I hate that definition because it's really just not intuitive at all. I think it's one of the best examples of how the formal definition of something can be a total pain, but intuitively the operation is super easy to understand. So let me give you the intuition again. Here's the example. Always keep this in mind. If I do AB tensor CD, how do you compute the tensor product? It's very simple. You just fix the first component A and multiply this matrix. So it's just A times CD and then B times CD. Okay, so now let me expand it out. Then you get AC, AD, right? That's the first vector, first copy of CD, and now the second copy of CD, you get this. Okay, so that's just the tensor product. And that definition kind of straightforwardly extends to matrices too, right? There's nothing special about vectors here. Just fix every copy on the left side of whatever's on the left-hand side and put in a copy of whatever object is on the right-hand side. Okay? And so this kind of multiplicative behavior, by the way, right, this thing here that you multiply dimensions, this is why if I take the tensor product of, if I take C2, a single qubit, and I take n copies of this, right, n copies, then kind of the space I'm working in, right, is I keep multiplying the dimension, 2 times 2 times 2 times 2, and so that's why, remember, we get to this exponential size dimension for an n qubit system. This is the whole reason why quantum computers exist in some sense, because writing down these vectors directly is intractable, so you cannot understand how quantum mechanics behaves very nicely on a classical computer. So the hope, at least in the 80s, which kind of started this whole revolution, is maybe by building quantum computers we could simulate these extremely large vectors directly in some nicer way. And the goal there was to understand physical systems more than anything. Okay. So there are a whole bunch of properties of the tensor product here, which I don't want to write down. I recommend you look at the notes, so equations 14 through 18, right? Again, I don't think this lecture is complete without looking at the notes because it's just too long to cover in one lecture slot, right? And I'm just going to end up copying 5 equations on the board, which is a little bit ridiculous, right? So I'll let you just kind of read that on your own and digest that at your pace. But these are things like this, right? Kind of basic properties like, I'll just write down the first one to give you a sense of what we're talking about here. The tensor product distributes nicely, so it's AC plus BC. Okay, and whenever I write this, remember there's an implicit tensor product, which I'm just refusing to write in order to save precious seconds, right? And that's standard in the field. Okay, for a very, very quick example, just to do something concrete so it's not always waving hands, let me remind you that let's do a fixed example, right? Ket 1 is this one, right? And what is the plus state? Well, remember that's just 1 over root 2 times 0 and 1 over root 2 times 1, so it's this thing. And now if I take the tensor product of these two, well, remember it's 0 times this vector, so I'll get 0 and 0. And then I concatenate that with 1 times this vector, which is 1 over root 2, 1 over root 2. Okay? And by the way, you could rewrite this exactly like this, right? It's just, not 0, 1, sorry. 1, 0, 1, 1. Oops, there's a plus here. Right? In terms of the basis for C2, written in binary, it looks like this. Okay, and that's exactly what you expect. This is the indexed by, the strings that index this are 0, 0, 0, 1, 1, 0, and 1, 1. Okay, and these are the ones you're seeing here. Okay. So that's how that works, just as a reminder. And so intuitively, I've used a fact here, right? Why have I assumed that I could write things in this kind of binary way and then still refer to kind of like the third and the fourth entries here where, this is in decimal, this is the number 3, this is the number 2 in decimal. And of course we start counting at 0, so this is the third and the fourth entry, respectively. Well, the reason why I was able to do that is because when I take two bases and I take their tensor product, the result is a new basis for the bigger space. That's what I've implicitly done here. This is equation 29, and I'll get you to think about that on your own. But basically for orthonormal bases, B1, which maybe let's just take 2 vectors for now, and B2. Okay, and these are of course going to be now in C2, because I've only got 2 of them. Well, they could of course be in a higher dimensional space where I don't fill out the full space. It's not a basis for the full space, but the claim now is that if I take the pairwise tensor product of all these guys, like psi 0, tensor phi 0, right? Psi 0, tensor phi 1, and now psi 1, tensor phi 0, psi 1, tensor phi 1. If I take all 4 of these, that's going to be an orthonormal basis for the bigger space in which the tensor product lives, right? Each of these guys lives in C4, basically, and so this turns out to be a basis for the bigger space C4. And that's why over here, when referring to, this third element of this matrix, I could write it as, instead take the basis for a single qubit, 1 and 0, and then tensor product them together to get strings of length 2. And then this will correctly label the third element in my vector now. This will be the fourth element. Okay, this is the fact I'm using up here. Good. All right. That's composite systems. No discussion about composite systems will be complete if I don't mention 2 more things, right? Which are quantum entanglement, right? And the notion of a 2-qubit gates, right? I mean, if all we did was single qubit gates, that would be extremely boring. And certainly you wouldn't do anything non-classical in any real sense. You could all simulate it on a classical computer. So 2-qubit gates are incredibly important. And the reason why they're important in some sense is because they allow us to generate entanglement. So let me first remind you what I mean by entanglement. Okay, so the basic idea is that, recall from what we just learned above, that if I take 2 vectors in a smaller space, like psi 0 and phi 0, I can stitch them together to get a vector in the bigger space, right? So I can take psi and phi in each in CD, and I could stitch them together to obtain psi tensor phi, which is now in CD squared. Okay? I can always do this. I could always construct a bigger object out of them. The converse is not always true, meaning so there exist now states, let me give it another name, let's say eta, right, in CD squared, right, in the bigger space, such that there do not exist psi and phi in the smaller space, such that, the tensor product gives you the bigger vector. Okay, so it's not true in general, remember, that this larger state can be decomposed as the product of 2 smaller states. Okay? And that's literally entanglement, right? And in the most basic definition. These are the ones we call entangled states. Okay? Okay, so that's the most basic definition. You cannot factorize it. We can say a bit more, actually. It turns out that you can understand kind of the amount of entanglement, especially for 2-party pure states, very well, right? There's this so-called Schmidt decomposition, which tells us everything we need to know. And it only holds, decomposition. Remember that it only holds for 2-party, so bipartite, like the way I have here. So there are 2 parties, pure states. This just says that for all states psi, or maybe I should use eta again to be consistent. Sorry, for some reason the eraser doesn't want to work. All right, well, fine. But there it goes. For any state psi, sorry, I wanted to say eta. It's the whole purpose of having the eraser. Okay, I'll just cross this off. Okay, so for all eta in the bigger space, right, so let me write it as CD1 tensor CD2. Okay, so you're living in this bigger space. I can always write eta is equal to the sum over I equals to 1, I equals 0 up to, now the minimum of the two dimensions, d1, d2, minus 1, of si times ai, bi. Okay, so let me just define a few things here, right? So remember, these are the Schmidt coefficients. And they're just some non-negative real numbers. Okay? These guys are the Schmidt vectors. And they form orthonormal bases, meaning that if I look at AI as a set, and I look at BI as a set, then these are both going to be orthonormal bases. Okay? And the key point here is that, in general, I can always decompose eta in this way, right, in terms of, two bases. But the point here is that the indices match, right? And when I'm indexing AI and BI in the tensor product, you'll notice that, I fix some, the Schmidt decomposition says there's a particular ordering of these basis vectors. So, A1 and A2 and B1, A2, B2, so that you can kind of pair them together in this way. And you can reproduce the state eta, okay, by having non-negative elements here. So the Schmidt decomposition is crucial, and it tells us basically whether or not our state is entangled, right? Because the Schmidt rank of the state, remember, is the number of non-zero Schmidt coefficients. Okay, it's a number of SI here which are not zero. Okay. And if you're wondering, by the way, does the Schmidt coefficient have anything to do with the spectral decomposition? And the answer is sort of. It's really more accurately tied to something more general than the spectral decomposition. It's called the singular value decomposition, which you may or may not have heard of I think we talk about it in the intro course, but regardless, that's where the Schmidt decomposition really comes from. I'm not going to get into it here. Okay, so the Schmidt decomposition not only tells us whether a state is entangled, right? If you're not entangled, then you can be written as a product. That means your Schmidt rank is, oh, sorry, I haven't written it down. But intuitively, if you're a product, that means that your Schmidt rank is precisely 1, right? There's no sum here, right? It's just one term. It's just AI tensor BI. That's a state that's not entangled. As soon as you are entangled, right, you can't be written as a product, then we need multiple terms in the sum. And that's why we say that eta is entangled, if and only if the so-called Schmidt rank is strictly larger than 1. Okay, you need at least 2 terms in the sum. Okay, and so the canonical example of entangled states, at least on 2 qubits, are the Bell basis in C2's tensor C2. Right? These are worth seeing because we will go over these. We will use them, right? So phi plus 1 over root 2, 0, 0, plus 1, 1. Phi minus 1 over root 2, 0, 0, minus 1, 1. And then we have psi plus and psi minus. Sorry, this is the plus. 0, 1, plus 1, 0. Okay, so these are the canonical entangled 2-qubit states, if you will. They're all kind of maximally entangled in some well-defined sense, which I will not state here. One thing I should mention is that the Schmidt decomposition, right, which gives us a way to tell if a state is entangled or not, because you just remember a state is entangled, a bipartite pure state is entangled if and only if its Schmidt rank is at least strictly larger than 1. The Schmidt decomposition can be efficiently computed, right? It just turns out to be the so-called singular value decomposition, which can be efficiently computed. So that gives us an efficient test for whether a state is entangled when you talk about two-party pure states. More generally, if we're going to start talking about two-party mixed states, it turns out that detecting if a state is entangled is actually not efficiently solvable. It's NP hard, okay? So we'll talk about mixed states in a second, but just as a quick heads up, in general, it's hard to detect entanglement. Okay, so my whiteboard froze up on me, so I just wanted to pull up a new one, since we're going to talk now about 2-qubit gates. Okay, so like I said, if we just had competition with 1-qubit gates, it's not very interesting. 2-qubit gates are going to be what makes life fun. And there are 2 types of 2-qubit gates, right? 2 types. So the first type, remember, is just going to be take the 1-qubit gates we already learned, like Pauli X and Y, and then take their tensor product. Okay, so a tensor product of 1-qubit gates. Okay, so for example, you could do something like X tensor Z. That's going to now be a unitary operator acting on C4. And the generic formula for this goes exactly as you think. There's A, for example. Here's B. These are just 2x2 matrices. And if I take their tensor product for completeness, remember, it's super simple. It's just going to be, take the first guy and put in a copy of B, take the third guy, in this case, put in a copy of B, and so forth. Okay, and when you expand out B, right, you'll see that you'll get an operator that acts on C4. It'll be 4x4 instead of 2x2. So the tensor product for matrices is, extended in very naturally in this way to be defined on matrices, right? There are 2 additional rules that I do want to mention that are nice for matrices, which are that if I have A tensor B times C tensor D, then you get AC tensor BD. Okay, so typically we'll think of this kind of as these will be kind of system 1, if you will, like the first qubit, and these will be system 2, remember? And what this basically says is that everything on system 1 kind of comes together, everything on system 2 comes together. Right? So in system 1, I had this one and this one, A and C, those are the red ones. And indeed, here you see them together on one side, and here you see system 2. Okay? And that's just saying that, I guess I'm going to do this in a second, but that's just saying that, if I had wires like this, right, where I had A on the top, let's say system 1, B on the bottom, right, that's this first bracket here. And then I apply the second bracket, C over here, whoops, D over here, right? Well, what does this look like? Well, this is completely equivalent to, I can think of these guys, well, maybe I shouldn't do it that way. I can think of them as, a joint operator AC on the first wire and a joint operator BD. I mean, the order switches, of course, remember when we write it. Did I do this right? I think that's right. No, technically I wrote it backwards. I should have written it, sorry. Remember we switched the order, right? Because the operator, if I put a vector on the right here, right? The operator which hits the vector first is the one on the very right, not on the very left. So technically speaking, I need to swap the order of these guys. So let's do that. So first let me do CD. Right, that's technically the first gate on the first and second systems, and then we apply A. And here we apply B. Okay, and so on the first system, right, the first wire, then you're going to get, first you apply C, then you apply A, and that's what you see here, right? First you apply C, then you apply A. And likewise on the second wire, on the second system, first you apply D, then B. Again, here you go. First you apply D, then you apply B. Okay, so things kind of bunch up on the wires. That's all this is saying. Okay, so let me just remind you, for example, that if I have the trace of x tensor x times x tensor x, just as a cute exercise, this just says something very simple. It's just the trace of x squared tensor x squared, right? Because each copy of x will multiply these two copies together, these ones together. And remember, x is self-inverse. It's a NOT gate. If you do NOT twice, it goes back to identity. So this is the trace of identity tensor identity. And then, if you want, you could write it this way. Oh, that's the second identity I wanted to remind you of. So good thing we just did this. Second identity I wanted to remind you of is this one, right? Which is that the trace of A tensor B is equal to the trace of A times the trace of B. So it plays nicely with this tensor product. So anyway, going back to this equals to 2 times 2, right? Which is 4. Because you have a 2-dimensional identity on each side. Okay, so I just wanted to remind you of these two properties, which are useful and we'll use over and over again. Okay, so just as a sanity check, circuits, I'll just do a few examples just to make sure you remember how this goes. So if I have x tensor I, the corresponding circuit is on the first wire I do an x, on the second wire I could put an identity gate, but normally we just won't write anything because we don't do anything. If, for example, I say identity tensor z now, oh, sorry, I forgot, I'm supposed to say z, right? Identity tensor z, okay, that looks like this because I only act on the second system. And instead, if I do say Hadamard's on both systems, well, then that's just saying this. Okay, ta-da, that's it. Now, the other type of gate, this is the first type of gate, right? The first type of 2-qubit gate, remember, is a tensor product, like this, x tensor z. The other type of gate is something that's genuinely a 2-party operation, right? It can't be written as a tensor product of 2 smaller gates. So maybe this is what I'll call, genuine 2-qubit gates. And of course, these are just some unitary now, which are acting on C4. And kind of the canonical example of this, right? Maybe I should also put a thing here. The canonical example of this thing is the C0 gate, control NOT. Control NOT, also known as the C0. Okay, and again, all I have to do to specify a linear operator like the C0 is I just have to tell you its action on my favorite basis of choice. By linearity, then you know exactly how the operator acts on the entire space. So this is defined as follows. C0 of 0, 0 goes to 0, 0. C0 of 0, 1 goes to 0, 1. C0 of 1, 0 goes to 1, 1. C0 of 1, 1 goes to 1, 0, right? Okay, so all this is really doing is, remember, it looks at the first bit over here. If that control bit is 0, it does nothing to the second bit. And otherwise, if the control bit is 1, then it flips the second bit. Okay, so that's why 1, 0, the control bit is a 1, the target bit is 0, then it goes to, control bit stays the same, but the target bit is now flipped from 0 to 1. And I'll let you think about what is the matrix representation of C0, right? If I write it as a 4x4 matrix, what does it look like? Okay, just think about how we defined writing down the matrix representation of a linear map once you know its action on a basis, and that's exactly what I've done for you here. In terms of a circuit diagram, it just looks like this, right? We say this is the control and this is the target wire. Okay, so that's like the first qubit in this picture, right? And this is the target wire, the second one. So this is this second qubit in the picture. Okay, that's always the ordering we use in this course. Okay, so in particular, let's just refresh your memory with a concrete example. If I do C0 on the Bell state, right? What does that do? Well, remember that this is just by linearity. It's going to be 1 over square root 2. The Bell state was just 0, 0 plus 1, 1. So by linearity, I can write C naught applied to 0, 0 plus C naught applied to 1, 1. And now, again, we condition on the first bit. The first bit 0, nothing happens. Now the first bit is 1, and so we flip the second bit. Okay? And if you stare at this long enough, you'll see that this is nothing other than, remember, plus the tensor. Now it's a tensor product state. So even though the Bell state is not in tensor product, when I apply the C naught, which is a genuine two-qubit gate, remember that it can kind of decouple these qubits and turn them into a tensor product, which is what we see here. Okay, good. So the last postulate that I want to review, and then after that, we'll just briefly review how everything generalizes to mixed states, which will require very little new definitions, is the measurement postulate. Okay, so remember the basic idea here is that we know how to describe states. We know how to do things to the states to make them change, evolve, basically. But ultimately, a computation is useless unless I can extract information out of my system. And that's what a measurement is for. Okay? So a measurement or an observation. So kind of the most basic type of measurement, so this is, sorry, to extract info from the system, to read out, for example, the answer to your computation. The most basic type, and actually it's not really the most basic type in the sense that, without loss of generality, any measurement can be phrased in this way, right, is the so-called projective or von Neumann measurement. Okay, and the way you define these measurements, remember, it's a set of projectors, hence the name projective. So B equals to pi I equals to 0 up to m. Okay, so they're just a bunch of projectors, right? So that means, remember, pi I squared equals pi I. And we need a very special condition to hold in order for this to be a well-defined measurement, which is the so-called completeness relation, meaning if I add these guys all up together, they should give me, the d-dimensional identity, whatever dimension the space is. Okay, so this is the completeness relation. Okay. And the special case of this that we will often use in this course is, each of these projectors, they could be a high rank operators, but the most basic case is when if each pi I equals to, some state psi I. So it's basically rank 1. The rank of pi I is equal to 1. Okay, so whenever these guys are all rank 1, then we say we measure in the basis psi I. Okay, so I have these projectors, they're all rank 1, they sum to identity, so I know that they are a complete orthonormal basis for the space. So then doing this projective measurement, remember, is what we say, what we call measuring in that basis psi I. And so normally, the most standard example is the standard basis, right? So a measurement, therefore, in the standard basis, okay, is what? Then I would write B, and what are my projectors onto each of the standard basis vectors? They look like this. I equals to 1 up to D. Sorry, this is for CD, right? Oops. That's it. Okay, and these are all going to be in CD now. So that would be the set of projectors for a measurement in the standard basis. So that's how we formally define measurements. Like any such set of projectors, remember, is a measurement. And a measurement makes no sense unless, I talk about formalizing the probability of a certain outcome when I make the measurement given a certain state. Okay? So given state psi and a measurement, a projective measurement, let's say, which is I think everything we'll use in this course. Okay, so given a state and a measurement, what are the probabilities of getting each outcome when I make this measurement, right? Then the probability of outcome I, right, when I measure in this basis, or when I measure with respect to B, given state psi, right, is equal to the trace of pi I psi pi I. So you stare at this for a second. All this is really saying is that, if I have a state psi, I hit it with a projector, which kind of pushes you down into some low-dimensional space, and then I measure the length of the resulting vector, essentially. I mean, it's technically up to a square, but that's the basic idea here. Okay, so in particular, if my state psi lived fully in the support of, the first projector pi 1, then, when I hit my state psi with pi 1, nothing would happen. My state would still be psi. I wouldn't lose any of my norm, and then the probability of seeing that outcome would be 1, right? Because I live fully in the space that pi 1 projects onto. So I'm just going to move this over, psi, and it's a projector, so I can write it as this. Okay? So that's the probability of each particular outcome of my measurement, pi I. So there are two things I need, right? And the second one is, what is the post-measurement state? Right? Remember in quantum mechanics, when we measure, depending on the outcome, we change the system, right? In general. So the post-measurement state is the following, psi prime. I take the state I start with, right? And then, if I got outcome I, okay, so upon outcome I, let's be clear. Okay. I got outcome I, so I project down onto pi I, whatever space that is. And the problem is that pi I times psi, if I'm pushing you down into some low-dimensional space, I'm cutting off part of this vector, essentially. This thing is not normalized anymore, so I have to renormalize it in order to make it a unit vector, right? Otherwise, it's not a valid quantum state. So I just divide through by its norm. And if you just expand out the definition, you'll see that this is just this thing here. Okay. And so let me just remind you, exercise 36, right, which says that if I have psi like this, alpha 0 plus beta 1, right, and we measure in the basis b equals to 0, 0, the standard basis, basically, that's the standard basis, right? Then we obtain, the probability of outcome, for example, 0, we'll just do one of them, right, is equal to what? It's the trace of 0, 0, right, times the state psi, okay? And if you work this out, you'll see that what you'll get is the absolute value of alpha squared. Okay, so I encourage you to work that out and to see that this is indeed what you get. Okay, and same thing if I say probability of outcome 1, then here you'd get beta squared. Okay? So in this sense, of course, the larger the magnitude of the complex number in front of 0 or 1, the more likely you are to see that outcome when you measure in the standard basis. Okay, finally, the circuit symbol for measurement is just this thing. Psi goes in, right? And we use this funny measurement meter, if you like. Sometimes we don't do it that way. Sometimes we also write it this way, right? We just put this. And both of these mean, let me be very clear, measurement in the standard basis. Okay, so we always mean measurement in the standard basis, Remember this without loss generality, because if you want to measure in any other basis, you can always first do a unitary to map yourself into the standard basis and then measure in the standard basis. Okay? That will always simulate a measurement in any basis. Okay, that's all I want to say about pure state computation. And now I'm going to remind you of mixed state computation, and we can close. Okay. So the basic name of the game here will be, just to briefly tell you how these postulates, remember, generalize to the mixed state setting, and it'll be kind of very natural how this works. Quantum computation. And remember that a mixed state basically is what happens when I don't know exactly which pure state I have in my possession. You know, at random I get some state, and so there's some uncertainty in my state inherently. Okay. So the main difference to model this, remember, is that instead of talking about pure state factors, now my states are represented by matrices. Okay? So a mixed state is represented by a density operator. So represented by a density operator. Okay, so that's the keyword. Rho. Okay, and it's going to be some linear operator acting on CD. Okay. And in particular, what's going to be true is that any density operator by definition satisfies these two things. First, it has to be PSD, positive semi-definite. So it's a Hermitian operator where the eigenvalues are all non-negative. And second, it has to have trace 1. Okay? And intuitively, the reasons for these will be because these will make sure that when I measure this state in my favorite basis of choice, the measurement statistics that come out will form a valid probability distribution, meaning, you know, the probabilities will sum to 1. That's what the trace is going to give me. And the probabilities will be non-negative. That's what the PSD condition gives me. By the way, PSD means positive semi-definite. Okay. So what do these two things mean? This means that in terms of its spectral decomposition, I could write rho as the sum over I, pi, psi I, psi I. So these are supposed to be the eigenvalues in the eigenvectors. And because it's trace 1, right? Because it's trace 1, remember we showed that the trace of an operator is going to be the sum of its eigenvalues. So what do we know? We know that the sum over I of pi is equal to 1 by this trace condition right here, this one right here. Okay? And the way you should interpret this, right, is that, by the way, and the other thing is that this is non-negative, right? So that's also, we also know that for all I, pi is greater than or equal to 0, and this is by 1, right? That's this one up here. Okay, eigenvalues are all non-negative. So that's why the eigenvalues form a proper probability distribution. The way you should interpret this, remember, is that it's like saying, you know, I flip a coin or a, you know, a high-sided die or something like this, and with probability pi, I prepare the state psi I. Okay, that's what this is saying. It's that type of experiment. So it's like a mixture between, you know, quantum uncertainty, which is what you get out of entanglement, and classical uncertainty, which is what you get out of just randomness. Okay. So, you know, I really want to clarify. I mean, if you've seen quantum computation before, this is going to be kind of naively obvious to you, but you know, if I think about what we were talking before, which is this thing, right? A plus state, for example. Remember, this is just a column vector. Looks like this. Okay? But if I instead think about the mixed state now, which is 0, 0, plus 1, 1, right? Superficially, the notation looks quite similar, but now this is a matrix, and it looks like this. So they're really two very different objects in the end. Okay, and so exercise 39 will get you to work out what is the density matrix rho psi psi for an arbitrary state psi on a single qubit. Okay? So that's something just for you to work out if you've forgotten how this goes. A very special mixed state is the maximally mixed state. Okay, and what this basically says, remember this is just saying that it's rho in CD, sorry, it's a linear operator acting on CD, right? And the specific operator it is identity. And it can't be identity exactly because remember I need the trace equals 1 condition. So identity is certainly positive, right? All the eigenvalues are 1. I need the eigenvalues to sum to 1. So therefore, I need to divide through by the dimension, d. And the maximally mixed state is the state of essentially no information, right? If my state is in the identity basically as a state, then it basically tells me that I know absolutely nothing about my state. It's just completely random. It's like a random high-dimensional bit. So why is that kind of the interpretation we take of the maximally mixed state? Well, remember it's because if I take, for all orthonormal bases, psi I equals to 1 up to dimension d, right? If I sum them and add them, if I look at their projector basically, right? 1 up to d, that always equals to identity, right? The identity diagonalizes in every single orthonormal basis. So I know absolutely nothing about my state, right? I don't know which eigenvector I'm in, and even if I did know in some sense, like I don't even know what basis the system should diagonalize in, right? It's just complete noise. So this is a very nice identity, by the way. You should always keep in mind that when you sum up, when you look at the projector onto any set of orthonormal vectors, you'll always get the identity. Okay. Okay, so, and let me just be clear, it was sort of implicit here, but pure states are rank 1 density operators. Rho equals psi. Okay, so this is a if and only if, right? So if I have a rank 1 density operator, it's corresponding to some pure state. Okay, so now that I've talked about entanglement, right, and I've told you about the maximally mixed state, and I've told you about density operators, now I can tell you about the partial trace operator, which is our operation, which is how we deal with the fact that if I have a 2-qubit entangled state, right, normally it's not clear at all how to describe what just one of those 2 qubits, what state that is in, right? They're entangled, they're highly bound together, so individually they might not really make much sense. So we can't use pure states to describe them, we have to use mixed states. Okay, so remember the partial trace. Instead of writing just trace, let's say I have a bipartite system. What it will do is it'll take in a 2-party system, right? CD tensor CD. Let's imagine I call this system A and this is system B. It's going to essentially throw out the second system and keep the first one around. So it's not going to take me all the way down to a scalar like the usual trace. It's just going to take the second system down into a scalar. The first system is still going to stay like a matrix. Oh, sorry, I should be a bit more careful. These are linear operators on the space. Okay. So what is the formal definition? The formal definition is this. If I take the partial trace over B of a state rho, and sometimes, we'll write rho AB just to be clear that this is a 2-party system. Then what we do is the sum over I, and we take the standard basis up to D of identity on A. So I do nothing on the A system, but on the B system I project you down onto the ith standard basis vector. Okay, so this is the partial trace where I'm tracing out the second system. Okay, and here to be clear, rho AB is a linear operator that acts on CD tensor CD. And again, the dimensions don't have to match the local dimensions. I just chose to make it so in this example. So as a nice example, right, which I will not really do here, remember that the partial trace of the identity over 4, right, the 2-qubit maximum mixed state, that is going to be identity over 2, right? And in particular, actually what's true is that identity over 4 can always be rewritten as identity over 2, tensor identity over 2. Okay, you could always stitch it back up that way. Okay. By the way, there's another kind of equivalent definition of the partial trace. So I like this definition just because it's kind of clean. But there is another definition. That's technically exercise 41 in the notes, which is that you can also define the partial trace, if you like, this way. That if on any tensor product operator, I could rewrite it as rho A times the trace of rho B. Okay, that's a completely equivalent definition. You can go ahead and prove that if you like. Just assume this definition and show how this definition comes about. Okay? And in some applications, this is a bit nicer to work with. Okay. So let me briefly show you how to play with the partial trace on 2 examples of states that are worth recalling. So we talked about product states already, which is like psi tensor phi. The mixed state analog of that will be separable states. And these are the ones where basically it's now a mixture or a distribution over these product states. Okay, so basically it's a distribution over some state psi I tensor phi I. Okay, so non-entangled states, but I flip a coin and I pick one with some probability pi. Okay, so you might write something like rho equals sum over I of pi, right? So that's the probability, and then you would get psi I. Okay, the first time let me write it like this, right? On the left, and then psi I phi I on the right. And then remember that applying the rules of the tensor product, I can just put things together in a much nicer way, which is this. Okay, so now we're really talking about system A here and system B. Okay, so this is a separable state. It's mixed. It's still not entangled in any sense. And in these cases, it's very nice and easy to write down the partial trace. So if I take, say, the partial trace over B of rho, and again, let me think of this as rho AB over here. What is this? Well, in this case, it'll actually be easier to use this definition of the partial trace, right? It's just by the linearity of the partial trace, just like the regular trace, it's linear. It equals to this thing, right? Times, and here I'll put in the trace of phi I. Okay, so that's literally me applying this right here. And this is just equal to 1, right? Because cyclicity says I can move the phi I around. The inner product of phi I with itself is just 1. Okay, so that means I'll just get sum over I, pi, psi I. So for separable states, it's very easy to just immediately write down the partial trace, right? You just take this operator and you just kind of cut out this part. Okay. But what happens if I have something like a pure entangled state? And I want to talk about partial trace. Okay, so suppose for a second instead that I wanted to talk about, say for example, the phi plus state. Right, this does not factorize, so it's not clear at all what the local state on system A or B was supposed to be, right? And so how do we figure it out? Well, again, the only right operation it turns out to use that will correctly reproduce the measurement statistics after we do the partial trace, after we throw out a system, is the partial trace. And so if we throw out, let's say, the second system of the density operator phi plus, right? I encourage you to work this out. And you'll see that, and it's worked out in the notes, by the way, but do take a moment to go over it. You'll see that what you'll get is a half times identity on A, right? So this is on A and B. So, this is on AB, this is on AB, right? So in other words, the Bell state is so kind of tightly bound together that if I throw away half the Bell state, even though together I knew exactly what state they were in, right? They were in this state. Individually, they look like complete noise, right? They make no sense without each other. Okay? Good. So that is basically the maximum mixed state, partial trace. And now let's talk about how in this last brief section, how do everything we've talked about, how does everything we've talked about, operations and measurements on mixed states work? Okay, we only talked about so far in terms of pure states, but how does it work on mixed states? Well, remember that it works like this. So I'm just going to kind of put a little bit of a note in each section. So composite systems. So just like before, if I had two density operators, row A, row B are density operators. Then just like before, if I take their tensor product, I'll still get a density operator. Okay, so prove this, right? Prove. This is exercise 44. Okay, so go ahead and prove this, right? Because you have to check two things, right? You have to check that assuming these two guys are positive semi-definite in trace 1, you want this thing to be positive semi-definite in trace 1. And the trace is pretty easy to do. The positive semi-definite part is slightly more tricky, but again, the spectral decomposition will be your friend here. Okay? So again, do these exercises. Make sure you can do them all fairly comfortably, because then you'll be set up for the rest of the course. Otherwise, you might have some difficulty, and you don't want to go there, right? It's better to set your, you set your cards up in a row so you can knock them all down, right? Or whatever the saying is. Okay, unitary operations, how do we generalize this idea? Unitary ops, right? So for a density operator, rho, and here I'm going to start using this notation. For density operators, I'll use this kind of calligraphic D from that one. And for unitary, U in CD, right? So the action now, before, remember we just hit our vector, our pure state vector with U. Now it's quite similar, except we have to do it on both sides. So after the evolution, we look like U, rho, U dagger. Okay. Measurements. So for a projective measurement, B equals to the sum over pi I equals to, let's say, 0 up to m. And these maybe live in CD, or act on CD. Applied to the density operator rho, it acts on CD. The probability of outcome I is nothing other than the trace of pi I times rho. That's literally the old formula. I mean, I think the formula should be here somewhere, right? Where did we put that formula? Here, this is the formula, right? Trace of pi I times the rank 1 projector onto the pure state. And now we just generalize this to higher rank density operators, not a rank 1. And that's why we get exactly this formula here, which is the trace of pi I, and now we put a more general density operator here. And the post-measurement state is rho prime. And what is that? Well, again, it's rho. And now I project on both sides onto pi I. Sorry, typo in notes. Okay. Pi I, right? And now we divide by the trace of when the probability of that occurring, right? That's exactly what you see up here, right? You divide by the probability of having seen that outcome. Okay, that's how the measurement postulate generalizes. And so I'm going to close this lecture by stating an exercise that I highly recommend you do. It is super important. Exercise 46. And it also has a nice physical significance, but we'll use this over and over again in the course. Prove that for any bipartite density operator rho AB and matrix M that's acting on B, right, the following holds. We can think of M as being hermitian, for example. If I take rho AB, and I essentially, you can think of it as measuring in the basis B, if you like, or M, sorry. That's equal to this, the trace out of A of rho AB times MB. Okay, prove this. So what is this really saying, by the way? If I think of MB example as, some measurement outcome, right? Suppose it's some measurement outcome on the second system. Then this is saying that, I have a joint system, and I'm just measuring 1/2 fit, and I want to know what is the probability of hitting, let's say, pi I, the ith outcome. Then this is saying that intuitively, that's completely equivalent to first throwing out the system you're not measuring, right? I'm not measuring A, right? I have an identity here on A. I'm not measuring A. I can throw out the A system. I can do a partial trace on that. And instead, then, whatever's left when I do the partial trace, I just measure that part with B. Right? And intuitively, this makes sense, right? If I have a two-party system, I want to know what are the measurement statistics when I measure on this side. Intuitively, it should have nothing to do with what's on the left side. Assuming I have this identity here, right? That's very important. If I did something like this, right? If I didn't have identity on the left, then this equality does not hold at all. Okay, it would be a huge problem. Okay? So really, it's because I'm doing nothing on one side. And so just as a quick hint for this, just remember the fact that I could always decompose the identity as a projector onto your favorite orthonormal of basis of choice, like, say, the standard basis. Okay, I believe that's it. All right, so that brings us to the end of lecture 2 on quantum computation review. Okay, so we've talked about basic linear algebra. We've talked about basic quantum computation, both in the pure state and mixed state settings. I highly, highly recommend you go through all the exercises in this lecture. Again, there's a lot I did not cover, right, in the actual physical lecture, or the video lecture, that is in the notes. Well, I shouldn't say a lot, but, a reasonable amount. So you really should read over these and do all the exercises. Make sure you're comfortable so that now we're ready to kind of move on to the proper new material in the next lecture, okay? Assignment 1 is out. Don't forget to have a look at that. It will be due right before tutorial next week. That's it. Please have a good week, and as always, please stay healthy.